Hello and welcome back to this latest video. In the last video we explored how to switch on and off, how to flip a single core bit of a magnetic core storage device. We were successful in doing that. We were able to flip a single core into a 1 or into a 0 state. However, in this video we're going to ramp things up a bit. We're going to basically construct a multi-bit memory core device. So let's look at this rundown here of the procedure that we're going to follow to get this job done. We're going to use the same core storage device, the Fuji unit that we looked at in the earlier video, but we're basically going to, as I say, ramp things up and get the whole thing working, get all of the cores working, all 288 of them. So this is what we're going to do. Number one, well, this is done, single core bit test. So let's just let's put a tick on there. Yeah, we did that. That was in the last video. Single core bit test. Then we're going to design a bigger array of cores. So we need to come up with some sort of a mechanism, a design. You know, probably just something conceptual like the blocks, the building blocks that we need to get this thing to work. How we're going to address, you know, the core storage device. There's different ways you can do it. I'm probably going to end up doing something like using 4 lines of binary for the X coordinate and another 4 lines, or possibly 5 lines depending on the array size, of binary for the Y coordinates, and we're going to address those from something like an Arduino or something like that to, you know, read and write data from the core storage unit. That's kind of what I've got in my head roughly, and we'll have a look at that closer in a moment. Point 3 is let's come up with some sort of schematic diagram. So we're going to go into KiCad, just like we did before on other projects. You'll find I use KiCad quite a lot. It's very good. We're going to design a PCB this time as well. So we're going to do a schematic and a PCB all in KiCad. Right, point 4, send the design to the fabrication house, get the PCB actually built. We are going to populate it. Point 5 is let's test the thing, let's power it up and debug, because you can guarantee it's not going to work first time. There may be some adjustments we have to make. Finally, we're going to write some software both for the Arduino microcontroller unit. That'll be doing very low level pulsing, you know, sending binary data to the core store design, some sort of like parallel cable using 4-bit and 5-bit binary, and we'll have some sort of clocking or enable pins, that sort of thing, to tell it to write or to read from the core. And at the very end we'll have some sort of a GUI, a graphical user interface, and from that we'll you know, hopefully get that far, we'll get something on the screen where we can flip bits on and off, and we should be able to see it visually. So that's kind of what we're going to do in this video. So as I say, point 1's done. We've already got the single bit out the way. Let's go and design a bigger array for the cores. Let's look at this conceptually, just in a block diagram fashion, so we can kind of get an idea of how we're going to approach this before we start actually designing schematics and what have you. So the first thing we need to do is understand the device that we're actually going to be dealing with. And in our case, this is the Fuji device that we have, which is a 288-bit magnetic core memory device. That means it's 288 bits, which means it's got 288 individual ferrite cores in there that can all be addressed using either these column drive lines, these wires that go through the cores, or the other way, using these row drives, which goes that way. When you put a half current through both of these lines, if you say selected this one here and this one here, where the currents add up, you would have enough current to flip the state of the ferrite core. But we've covered all that in the previous video, so I'm not going to go through it all again. So all we really need to know here is that we need to get current to go through these lines, either in the columns or in the rows, and you can call them X and Y if you want to. And we're going to need some sort of drive amplifiers in order to get the current to flow. We can't just use TTL signals to put through here. You know, you look, if you get like 10 or 20 milliamps from a TTL chip, we're going to need at least 150 milliamps or more in each of these lines in order to get the half currents that we need. So, and on this particular design, it's a little bit unusual to other core storage devices that I've seen on the internet and what have you, in that we have common connections. What that means is all of the drive lines that go through actually have, at the far end, they're all connected together, and we have a common for the column drive, and we have another common, a separate common. These are not connected together, these are separate commons. The other one is for the row drive. So instead of the lines coming all the way through and you end up with like 2 connections for each line, we only need drivers for one side of it, and the other driver is for the common, so we can flip the polarity one way or the other to change the state of the core. That's a little bit of a peculiarity with this device, and it reduces a lot of lines. It's not a bad thing. The other thing is, this particular device is sectioned into 2 areas, if you like. There's the bottom section, which has its own sense output connection. It has the sense loop, which is a diagonally fed through wire in our case to help reduce noise. The winding actually goes through sort of like an S shape, if you like, and they do that diagonally. If you remember, the drive lines are sort of in an XY location, straight like that. These go diagonally in order to reduce the amount of noise pickup when you select the lines, when you actually put current through and select them. Anyway, so this bottom half has this a pair of sense wires, which is the loop that goes all the way through, and the top half, which is the other, I think it's let me say it's 4 lines at the top. It's 12 lines at the bottom and 4 lines at the top. This has its own separate output. In order to detect the bit, like we did in the single bit experiment we did earlier, we do need a sense amplifier to detect this current. It actually develops about 50 millivolts across here, and that flips the state, and it's going to give us some sort of an output bit. Now what I'm thinking is, rather than having 2 sense amplifiers, one for the bottom half and the other one for the top half, I'm thinking we can probably just loop these in series and have 1 sense amp, because I'm going to regard this as one big core, and I'm not really bothered about the fact that it's 2 separate areas. That would have been something specific for the calculator design that it came out of. They would have done that for a reason, but we're not going to do it that way. So I'm thinking, right, address the whole thing as one big continuous block and put the sense wires in series. I think that should work, and have a single sense amplifier. Now, in order to address these parallel lines, if you remember, we've got 18 lines along the bottom. It's 18, if you like, columns being addressed, and we've got 16. It's actually 12 plus 4. It's 12 plus 4, so that's 16 parallel lines in the row direction. And in order to address these, remember, we need amplifiers to feed all of these lines, and there's different ways you can make amplifiers to do that. But in order to address those amplifiers feeding these lines, we're going to need some sort of decoders. I'm looking at using 74, probably HC series actually, 74154s, a couple of those, and that means we can put binary data into these 4 lines coming in, and that gives us 16 lines coming out. And also the same for the row drive. Okay, if you're following all this, you will realize that, hang on, we've got 18 lines here and we've only got 16 lines coming out of the 154, so we're going to have to tack on probably another chip like a 138, 74138 or something like that, to give us a little bit extra addressing capability, output decoding ability from the basic 154. This has to be another couple of lines. It's got to go from 16 to 18. So there's a little bit of jiggery we have to do to expand that, but just as a conceptual block, I hope you can realize this is how we're kind of going to do this. That's like an overall view. We're going to need some way of sending in like an enable bit, a clock bit, or something like that, in order to say, okay, once the address has been selected, in other words, our core has been selected, the one that we want, by putting the appropriate binary input on these, we need to say, okay, write a 1 or write a 0 and flip the state of that core. Okay, so conceptually, that's what we're looking at. And just to reiterate what we were saying earlier, just to make it a little easier to understand, so we're going to use these H bridge, or half bridge actually, the half of the H bridge, to activate the drive lines, to select, as we say, the drive lines, both in the X and in the Y positions. But the other ends are commoned, so we need another amplifier at the common end. All these are connected together up here, and all these lines here connected together here, so you only need one common for that direction and another common for the other direction. So you can see that by selecting any one of these drive lines and a common, you really can put the current through any which way you want through any line, and that's the whole purpose of the drive circuit for the core storage device. Okay, so let's look at a little bit more detail about the H-bridge driver, the drive amplifiers to the lines. And I've skipped a lot of the searching through. I'll spare you all of the pain of searching through different component specifications and different values, and then working out how, you know, rise times and internal resistances and all that nonsense. It takes a long time. So I've cut all of that out, and I'm just cutting straight to the chase here, and I'm going to show you the best solution I can think of for this right now. So I've decided to go the MOSFET route, using a couple of MOSFETs for the drivers. As I say, this could have been bipolar transistors, or we could have just used an integrated circuit chip solution for the whole thing. Well, there's a few reasons why I've chose this. One, with these being enhancement MOSFETs, you can drive them straight from 5 volts and 0 volts. We'll turn the gate fully on and fully off, and it's the same for the other FET down here. So these can be driven directly from the output of a HC CMOS device, like a 74HC whatever, 154, whatever it is, which is great, and it makes our life a little bit, you know, a lot simpler. I've decided to go for the NTR 4101. That's a P channel, and for the other side, for the N channel, I've decided to go for an NTR 4501. So it's a 4101, 4501. These are basically, they're pretty close. They're pretty much, they're not exactly matched, but they're close enough. And the best thing about these things is the internal, the R on, the internal on resistance, if you like, is it's something like 0.08 of an ohm. It's very low indeed. You know, 80 milliohms turn on. So when these actually switch on, you know, you can actually sink a fair bit of current, a lot more than what we need. This will be the drive line to going directly to one of the lines of the core device, and what we're doing here is we've either got a positive switch or we've got a negative switch. The other thing to realise as well is we have another one of these mirror imaged over this side, which will drive the common. So instead of being a drive line, it'll drive the common of the line itself in the core storage device, just by altering the 5 volt logic, if you like, high low of this pin here, and those two of the mirrored pins there. Those 4 pins can completely control whether the current is flowing through the drive line that way or whether it's flowing through that way, just by altering the state of those 4 pins. And that's really all we need to do for whichever column or row you happen to be in. Don't forget, this has to be replicated for each drive line. But what it does mean is we only need these for the drive lines, and the commons are just done once. So we actually only need 2 common amplifiers. We don't need 16 and 18 for the other end of the wires. That's a nice reduction, simply because the Fuji unit that we're working with is using common lines rather than making everything completely parallel. And that reduces a lot of the amplification circuit that we need. Quite handy. So we need 2 amplifiers like this for the commons, and we need a load of these, one for each drive line. We need 18 of these for the columns, and we need 16 of these for the rows. So yes, it's a lot of transistors, but you know what? That's how it goes when you're dealing with core devices. You do end up with a lot of circuitry. A couple of gate resistors just to limit input current. Typically, looking around at various other designs for switches and things, these tend to be about 100 ohms. It's best if you actually have some sort of like resistors on the gates. Right, onward. One other thing to consider with the drive amplifiers, because the lines are common, we can't just have like drive amplifiers that are always in either a positive or in a negative state. If you did that, because remember all of these drive lines are common at the far end, in our particular case on our device. Remember, not all devices are wired that way, but ours is. So the far end is all common. Now we can't have this where it's just, you know, feeding either, you know, a positive direction current or a negative direction current, because you've got lots of these all connected together. All of these are connected at the common, and what would happen is the current would simply flow through to the next drive amplifier, probably cause damage, because I mean it would just go straight through. There wouldn't be any current limiting or anything. You need to do a little trick, and well, the idea I come up with was we need a high Z, high impedance state for the amplifier. In other words, when this drive line is not selected, or all of the drive lines if you like are not selected, these outputs need to be in a high Z state, disconnected from the other amplifiers. And I had to think about that a little bit. Anyway, what I thought was, okay, well, it's quite simple. Just turn off both of the MOSFETs. Yeah, you have a waveform like this where the top MOSFET is at a positive input, which turns it off, and the bottom MOSFET has a negative drive, and that turns the bottom one off. So both MOSFETs are off, and the output's just kind of like free and dangling, if you like, high Z, high impedance. That means these can all be bussed together, which they are through the common, as I said, and there is no current flow anywhere. Only when the actual amplifiers are in the correct state, either a high-low or a low-high condition, then the amplifiers will switch on, either in a positive or a negative state, and that will go through to the common amplifiers. Now, in order to do this, to physically drive the amplifiers, we are going to need some basic logic gates to drive the gates of the MOSFETs, and we're going to work out a little bit of logic so we can select the line from a decoder and put it into its correct state, whether we need high Z or whether we actually want to drive it to a positive or a negative flow direction, current flow direction. So there's a few things to take into consideration. We need high Z, we need flow in one way, and we need flow in the other way. We need some combinational logic on the inputs here, and I've got a feeling we can do it with straightforward NAND and NOR or OR gates, that sort of thing. Nothing complicated, but we do need to work out the truth table to get the result that we want for the amplifier states. So looking at the combinational logic we need to drive the two MOSFETs for each switch or for each amplifier. So when the output of the decoder is in a high state, in other words when it's in a non-selected state, these two inputs are both high, which means you get a 1 through here, and that means this MOSFET will be switched off because it's a p-type, so that's an off position. That's an off logic state, and the high coming into here means we get a low, because it's inverted, get a low out of here, which means turn that off. So in other words, no matter what Q does, irrelevant of what Q's doing, the Q2 inputs, when the 74154 is not selected, we're in a high state, both MOSFETs are switched off into a high impedance state, which is kind of exactly what we want when it's not selected. It's only when the 74154 is in a low selected state, remember it's a negative logic output, remember it's like Y bar, whatever it's called, on the output Q bar. Only at that point is the logic gates able to allow through the data of Q0 and Q1, which sets up our polarity for which MOSFET we want to switch on and off. That's all well and good, and this can then be controlled from the Arduino input. So our Arduino development board is going to give us BCD or binary address lines which drive the 74154 to select which line driver we want, and the Q0 and the Q1 lines will set up the polarity of that line that we've selected, and that's what this bit of combinational logic will do for us. Yeah, so just expanding on the decoder logic. Okay, so this is our output of the 154, and you'll notice when the output is high, the MOSFETs go into a high Z state. But if you look at the Q0 and Q1 lines, which come from the Arduino controller, you'll notice that when the Q0 is high, nothing happens. Consequently with Q1, when that's high, it's only when the Q0 goes low for a duration or a pulse during the low state of the decoder being selected, which is this area here, then we get current going through the drive line. So this is actually sending current of a duration that we can set from software. This actually sends current through the drive line in a particular direction. Q1 is the same, basically sends it in the other direction. So these are our current controllers. These turn the current on for a set short duration. Typically about 1 microsecond is pretty typical for core storage. These pulses only occur when you want to put current through the drive lines. If both Q0 and Q1 are high, even if the decoder is selected, you don't get any current flow. You remain in the high Z state. And this is how we pass current through the drive lines during the decode operation. So the sense amplifier needs to discriminate the output from the sense wire within inside of the core store. This is how we read the bit out, whether the bit was a 0 or whether the bit was a 1 state. It's better to sort of describe it as a change of state indicator rather than it's a 1 or it's a 0, because it could be either. We're really detecting if it's flipped either from a 1 to a 0 or a 0 to a 1. This is a change detection really. Typically what we'd be looking at here in terms of time, this was like 0 and this would be 500 nanoseconds here. What we're doing is putting the current through the XY drive lines and trying to flip the state of the core. When we do that, the initial rush of current through the core lines does actually cause a little bit of noise. It's not much in our case, it's quite low because of the way that the sense wires are laid out in the core memory unit itself. In our case, it's what they call a diagonal sense wire. Kind of goes sideways if you like an S shape. And by doing that, you reduce this line noise quite considerably. It's actually quite small. But what you do get, if the core flips state, you get a nice signal over a certain amount of duration. It's not that long, it's probably about 500 nanoseconds in duration. But the important thing is that we're going to sample that at that point. We're not going to sample it here, otherwise you could pick up noise, and you're not going to sample it over here, otherwise you won't get anything at all. So you can actually adjust the timing point, or the gate if you like, of where we're going to look at the sense amplifier output pulse. So let's go over to KiCad, enter in our bit of combinational logic, our MOSFET switches, and get the line drivers going, and we'll have a look at the sense amp, and we'll have a look at the decoding circuit to decode the binary inputs to the decimal lines to drive the amps. So let's go. So let's open up KiCad and have a look at what I've managed to do so far. I'll open up the schematic, and of course yet again we're going to skip a lot of the hard work of entering in each individual component. If you've seen previous videos I've done, you can see how that's done, but basically this is what we've ended up with, and this is a fair amount of work. It didn't happen overnight. It took a couple of days to get it all properly correct. Here we are. Now I'm just going to briefly explain what's going on. So this is our input connector. This is taking our binary decode lines for the X select lines and for the Y select lines. We've got power at the top, which is a regulated 5-volt supply coming in, ground at the bottom there, and we've got these two lines here, which is Q0, Q1. These are our read-write lines, or if you like, which way the current is going to flow. Is it going to go forward, is it going to go backwards through the line? And we've got our sense data here on pin 14 of our connector here. So that's basically the all these connections here go to the Arduino board directly, pin for pin almost. Here's our decoders. These the 74HC. You'll notice everything I'm using is HC series to keep the current down, and it also ties in very nicely with the fact that we're using MOSFET logic levels. Enhancement MOSFETs work on 0 to plus 5 volt input gates, that kind of thing. So I've just kept everything HC for the sake of keeping it all neat. So yeah, we've got 74HC154. This is decoding all of the Y address, and you'll notice we've got our Y address coming in here, and we've got another 74154 down here, and this is giving us the X address with our X data coming, binary data coming in here. Now the X address decoder is very straightforward. It's 4 in and it's 16 out, and those 16 go to these amplifiers over there, which I'll explain in a moment. That one's very simple because everything's neat. 4 in, 16 out. It's exactly what we want. But on the Y side, you'll notice we've actually got 5 inputs here. We've got Y0 to Y4 because we need to address up to 18 lines, not 16. So we've got our 16 lines here, SY0 to SY15, our 16 address lines, but we need 2 more. If you remember what we were saying earlier in the sort of block diagram discussion I had earlier, we needed an extra couple of lines. So what I did was I've just added a 74HC138, and using this chip we get an extra couple of lines, and there they are, SY16, SY17, which takes to a total of 1 to 18 lines. All I'm doing here is I'm using the enable pin, which is enable on high. You'll notice these two have got, I'll just zoom in, these two have got little triangles on, which means they're negative going. This one does not, so this is a high going enable. This pin has to be high before this chip switched on, and that is connected to here, which is our Y4 signal. First 4 lines are addressing the DMUX, the 154, as per normal, giving us our 16 lines. And you'll notice when Y4 is low, the enable pin for the 154 is enabled. This is a bar. This has a little bobble on it there. So this is a bar input, which means it takes a low going signal to enable the chip. The other enable is just tied to ground, which permanently enables that one regardless. So when Y4 is low, this chip is switched on and these lines are active. But when the Y4 is low, it also switches off this one. So this one doesn't do anything. Okay? Now, when Y4 becomes high, in other words, we've gone from address 16 to address 17, if you like, we've flipped up to the next level, past the capability of the 154 here. This is onto the next 2 lines. So when this goes high, it turns this chip off and also turns this chip on. Now at this point, when this turns on, we're using Y0, Y1 and Y2 address lines through here, A0, A1, A2. This is our addressing scheme here, and we end up with another couple of lines. We actually have more than that. You'll notice these are all disconnected, they're not used. We could actually have more lines. If we had a bigger core storage device, we could potentially expand this a little bit further. So, you know, we can have a bit play with that. You could even connect LEDs to that for test purposes. Right, so that's all the decoding circuitry. You'll notice I've got some banks of inverters here, and what this does is gives you a maximum output current, in this particular case 3 times higher than what it would be if it was just a single inverter gate. This is really a buffering technique. It's given us a lower impedance output point here with a bit more current capability. And you'll notice I've got the same down here. This is Q0 coming in from the Arduino, and this is Q1 coming in. Basically these are getting inverted, and this one gets inverted to a Q1 bar. And there's another reason why I've done that, is because if you realize these Q lines here, the Q0 and the Q1 lines, these actually have to drive all of these drivers, all of these logic drivers here, and there's a fair amount of them, as you can see. The impedance of all of these added together, it's probably a reasonable amount of input capacitance to all of these chips. And to overcome that input capacitance and to help speed up the line transition from 0 to 1 and 1 to 0, we use buffers with a lower output impedance to drive them. And it basically, you know, it keeps the rise and fall times in line. They don't get too sluggish or anything. It's basically what they call a fan out. Basically the fan out of this is higher because we're driving a lot of inputs on the actual drive logic. These are our 2 XCOM and YCOM amplifiers. If you remember the core, it has 2 commons, one's for the X and one's for the Y drive lines. And these are the MOSFET drive lines that we've come up with for that. And these are being driven in such a way that these are actually inverted to the logic that we're getting to the drive lines. So when this one's high, the other one's low, sort of thing, and it means that the current works basically like a H bridge. This is the right hand side of the H bridge, if you like, and these are all left hand sides of the other H bridges for all the drive lines. I hope that makes sense. I'm rattling through this, and I hope that's actually clear enough to follow. Now all of these
are just repeats, lots and lots and lots of repetition here. So we only need to look at one. Let's just look at one. Okay, these are all the same, just with different labels and go into different lines. So here we go. You'll recognize this from our earlier discussion. We have our Q bar 1 and Q bar 0 lines coming in to our logic gates, and we're using a 74H332 OR gate, 74HC02 NOR gate. And the logic of these, which we've already figured out, drives the two MOSFET gates in the correct fashion that we need, depending on what we want to do. If you want the current to go that way or the current to go that way, by selecting Q1, Q0, and SX0 is the output of the decoder that we've looked at earlier on the right hand side there, and that's a low going signal, and that basically turns on this drive line. Okay, so that's got to be selected low before anything happens. When that's selected low, we can then change the logic level of Q1 or Q0, and that allows the MOSFETs to be driven. That's just one drive line, okay, and it's got the label here of DRVX0. These are just repeated for all of the other drive lines, and well, to be honest, that's the whole circuit. That's kind of it. So all of these are on the left hand side of the H bridge, and these are the commons on the right hand side of the H bridge. Okay, think of the lines as going between there. This is the core store device here. You'll notice I've got the sense terminals are actually wired in series. There's a series connection here, because if you remember, we've got two different sense wires. The core store was designed in a way that it's segregated into two areas, and what we've done is we've just put them both together, because I'm regarding the core store as one big block. And so that goes into the pulse transformer, and we've got the same pulsing circuit. It's exactly the same as the circuit I used in the previous video, where we're detecting positive and negative going pulses, using this little bias setup arrangement here to get the bases into the correct operating areas. These two transistors here, and I'm arbitrarily using whatever I had lying around. These are KSA 3265, KSA 3265 again, so a couple of NPN general purpose basically. And these are our switching transistors, which gives us our sense logic output, either a 0 or a 1. R77 here can be adjusted, and what I've done, I've put a variable preset on the board. I should have done that in the PCB design, but I didn't. Now you can set it up exactly on a scope, and you can get the bias point exactly right for maximum sensitivity and logic level response. Everything else is just drive lines. You've got all the X's down here, you've got all the Y's down here. That goes to all of the MOSFET drivers. And then we've got the commons here. On this particular device, you've got like the four corners of the unit are all connected to common. So I've just connected them all together. Internally, it's all connected anyway. It's like a PCB inside of the core device. This is just power. This sheet here is just, it's all chip power. Nothing to see. Lots of decoupling capacitors. I've got a lot of 10NF, because you know the rise and fall times of these things is pretty quick. It's like 20 nanoseconds. The logic's getting switched on and off quite fast, and you do get considerable pulses, both from the logic chips, from CMOS chips themselves, from HC series, and from the MOSFETs as well. So you know, there's a fair bit of current flowing through, and everything has to be properly decoupled. All of the chips have to be decoupled, and that's what this is here. So that's all this is here, and that's it. So that's our schematic diagram. The step after this would be to convert the whole thing into a PCB, so let's do that right now. Yeah, excellent. Okay, so we've done the schematic diagram, and again I've skipped out all of the actual putting the thing together. If you're familiar with KiCad, you've seen it all before. There's plenty of videos to show you how to put components onto the sheet and wire them up. I'm not going to go through all of that again. So let's just go ahead and look at the PCB that I've come up with. And I need to switch on some layers, because I've only got the fabrication layer showing here. Look at the fabrication layer first. You can see I've used surface mount components for everything, except where I couldn't, where it's actually our custom made pulse transformer. And you'll see all of these drive amplifiers here. So we've got 74HC32, 74HC02 logic chips. This is all logic, and we've got all of our MOSFETs and input 100 ohm resistors to the gates in these little banks of 8 here. So there's 8 in a bank here, 8, 8, 8, 8. These are the common amplifiers, and you notice there's our 2 load resistors there, our 2 current limiting resistors. So these are the two common amplifiers. We've got more line switching here, more amplification, and all of this down here. And on the right hand side we've got our connector coming in from the Arduino, nice big decoupling capacitor there, and we've got some 74LS154s and the 138 right at the bottom. This is all of our address line decoding. So you can kind of see all of these address lines are just going to go straight into these chips here, and then the outputs of all of these chips are basically going to drive all of the logic and all of the drive lines. The core store CM1 sits right in the middle here. So that's just the fabrication layout, so we can see with the components layout. Let's have a look at some tracks briefly. Front copper and back copper. So there's the board. Yeah, it looks nice. I hope it works nice. It looks nice. And so what we've got here, I'll turn off the fabrication layer, might help a little bit. Yeah, so you'll notice we're using it's all surface mount, and we've beefed up the positive 5 and the ground nets, so we've got bigger tracks for those to handle power, and signal is standard default track width, which is quite small. The drive lines are beefed up as well, so we've got thicker traces for the drive lines to handle the current through the core store, which sits right in here in these yellow pins there. And so all the drive lines are beefed up. Transformer sits down here, some through plated holes for the transformer to sit, and what have you. So yeah, that's our design for the PCB. It took a fair bit of work. I've really skipped over a lot of effort here. You know, first entering in the schematic diagram, and then, you know, getting all of the footprints for all of the components, you know, deciding which components to use in the first place, placing them all on the board, and running this all through the auto router. You've seen that in a previous video where I explained how to do auto routing, and this is how it comes out at the end of the day. You end up with a board like this, and this is now actually at the point where we can do a DRC, we can do a rule check, and everything comes out correct, and it's ready to upload to the fabricator. And hopefully the next section of this video will be some kind of board arriving in the post. That would be nice. That's just a bit of an overview of the PCB. We can go back to the schematic there. KiCad's great for this. You can flick between the two. You can go straight from schematic to PCB. It's all very good. Highly recommended. And it's free. Wonderful. So there you go. And that's our design. Let's see if the thing works.
Alrighty. Excitement time. The boards have arrived. Let's check these out. Okay. Oh, it's always an exciting time when you get new boards. Look at these. Oh my goodness me. If I can get them out the packet, of course. And of course I bought 5. I don't need 5, but I bought 5. Oh, check that out, man. Check that out. Woo. Core store device goes in here. Logic chips. MOSFET drivers in here. Lots of little surface mount stuff going on. And pulse transformer for the sensing amplifier. Hope you can see all of this. 74154s will go in here, and a 138 down there. Our connector, which will go to the power supply and the Arduino. Check that out. Wow. And that's just the back side of the board. Next thing is, let's get one of these populated. Alright, so progress, and here we are. All of the components are now being soldered onto the board. We've got all of the MOSFETs, and we've got the all of the logic chips, transformer for sensing circuit, and a couple of dropper resistors here. These are for the current limit. They may need to be adjusted when we actually come to power this thing up. I've set them for a higher resistance for now, just in case there's any problems. At least it won't blow up or anything silly like that. So the only thing left to do now, let's see, everything's in, is to put the icing on the cake, if you like, and get the memory unit soldered into position, and that'll complete the whole board. And of course, we've got the Arduino there as well, waiting to go, and that's all plugged in. So it really is just a case of getting this soldered in. I'm going to have to put a load of little wire links onto that, and we've got some bolt holes for the four corners as well, so that should get bolted in as well. Okay, so that's what we're up to. Let's see how this goes. So we've got the core unit, the memory core unit, now soldered to the PCB. There it is, and it's all bolted into position with all of its wires connected. Managed to find some bolts and a couple of little plastic spacers just to make sure everything's insulated. So I've also got little insulators underneath the legs as well, because of some tracks running by, so I just had to lift it up a little bit so nothing can short out. And there you have it. So the next thing is, basically that's now a complete board. That is it. So the next thing is we're going to give it some power, do some current measurements, make sure everything's alright, and let's see how it goes. Okay, so I need to interrupt the video at this point. Here I am in my edit suite, and I needed to tell you what had happened. We got so far with the project. I got the board built, as you've just seen, and assembled, and I did some preliminary checks before we went full on with the whole software and everything, which you'll see later. And I just wanted to tell you what happened. Basically, it wasn't working. I did some tests with the address bus, testing the X and the Y, and looking at the data coming back from the sample pin. And unfortunately, it wasn't working correctly. So we had to figure out what the problems were. It took some time, and I don't want to go through everything with you, but it was a problem, and it basically stopped the progress of the video. It turns out I was getting some sort of corruption from the Q0 and Q1 signals, and while I was writing to 1 or 2 bits, other bits in the core were being flipped almost randomly, like a noise, and couldn't really figure out what the problem was. So ended up changing the resistor arrangement to the current limiters on the common X and the common Y amps. So rather than having the resistors in the common lines, I decided to try putting separate resistors on the other sides of the drive lines, and so we had individual resistors going to all of the drive lines of the core, and it helped. So I was then able to get clean signals from the device, and so anyway, I hope this little explanation just shows you what was going on. Regard this as the debug section. It had to happen, and but eventually, because when we changed the resistors over, I believe it's something to do with ringing effects from the drive lines being switched on and switched off. Possibly the transient times are too fast. We're using very high-speed chips with high-speed switching MOSFETs. It could be the transients are just too steep, and we could be getting ringing effects, although when I looked at it on the scope I wasn't actually able to see anything. Now what I also did was remove the core store and just simply fit some LEDs and replace the drive lines with bipolar LEDs, so they either go green or they go red to show the direction of current flow. And by doing that, I was able to determine there was no obvious logic problem. Everything seems to work. We were getting current flowing in both directions, and there wasn't any crosstalk that I could see, interference from one to the other. So from a slow testing point of view, you know, not clocking it at high speed or anything, just in like half-second intervals, we couldn't see anything which was causing a problem. And on the scope, looking at the current going through the drive lines, that looked also clear and nothing obvious. Couldn't see any transients or even ringing for that matter. So the whole thing's been a little bit of a mystery, and I just wanted to point that out at this point of the video. But we did manage to sort the problem and mitigate the noise or whatever the problem is by putting the resistors at the other sides of the drive lines, which involved soldering a lot of resistors to the core itself before the core went into the PCB. Anyway, that's a little bit of a diversion. Regard that as a debug session. Don't fully understand what happened, but we got there in the end. So let's proceed with the next part of the video.
So yes, we need some firmware to go into the Arduino. This will be handling low-level operations, in other words, setting up the binary lines for the address decoders, and also pulsing the current through the drive lines, either in a positive or in a negative direction. So let's take a quick look at a little bit of code that I've already put together here. Again, we're saving a load of time. I'm not going to take you through the whole thing. So here are our port pins that we've got set up. So we're going from D2 through to D13, which is conveniently all down one side of the board on a single side of the connections of the Arduino development board. That means that we should be able to connect a ribbon cable directly between the two units, between the Arduino development board and the core memory PCB, hopefully without too many crossing of wires, that sort of thing, and we'll see that later. Now, so these are the actual pins, as I say, from D2 to D13. So these pins here, D2 to D5, these are the X address lines. This will give us our binary to the 74154 decoders. So that sets up here. Then we've got these 5 lines here from D6 to D10, which equates to Y0 to Y4. And these are the 5 address lines which will be setting up the Y address for the cores. Then we've got these 2 pins here, D11, D12, we've labelled Q0 and Q1. These are the actual current pulse lines. And then lastly, we've got D13, which is our sense input, which comes from our sense amplifier circuit. There is another pin, A5 analog pin, which we're just using as a digital I/O. It's not being used as an analog input, it's not an ADC or anything. And all we're doing with that is we're just pulsing it for the purposes of calibration. We're sending a pulse for an oscilloscope, and we can use it as a trigger input, so we can see precisely the point at which the sense amplifier or the sense input pin is being triggered. So that's really just for our own, if you like, diagnostic purposes. Means we can fine-tune the code and get the sense point exactly in the right position, which is very handy. I've got a little bit of explanation for the protocol I'm using here. I've just come up with a protocol, very simple, where you can send commands to the Arduino for read, you can write bytes, you can fill memory addresses, or you could write a string. So you can actually send an ASCII string to the core. So this code, a lot of it is very similar to the previous video that we did, except now we've got the address pins added into the mix. So now we can actually set up the data direction registers for the Y and for the X address signals. I'm not going to go through all of this, but here's a brief description of what's going on here. If we send the Arduino a character R through the serial port, whether it's upper or lowercase, what we're doing is we're selecting the portion of the core store that we want. Now, because the core store is 16 bits long, it means we can fit 2 bytes of 8 into each 16-bit word. So what I'm doing here is I'm sectioning up the positions so we know which byte of the 16 to write to, whether it's the low section of the core or whether it's the high section of the core. So that's really all we're doing here, to try and maximize the amount of data we can store into the core. You know, we could have maybe just not bothered doing this and just write it from write bytes from 1 to 16, but you're missing out on half of the core's ability. So this kind of doubles the memory if you think about it. Not doubles the memory, but let's say it utilizes the entire core block. Now this bit of code here is reading back the pulse information, or if you like the logic state, from the sense amplifier, and what we're doing is we're filling up a variable called data, which is a character, a single character of 8 bits, and we're loading it up in this for loop here, 1 bit at a time. So we're reading out a single bit at a time from the core at the address that we've specified. We're reading in 1 bit at a time, and we're filling up this variable called data. In here we're basically building up an entire byte of 8 bits, one at a time. So that fills up that. When that bit has been completed and we've read that in, we then restore the bit back to its previous state. So now we're testing, if you like, the bit that we've just read in, called it test here, and we're taking the boolean of it, just whether it's a 1 or whether it's a 0. If it's not test, in other words it was a 0, in our case that means it got a pulse. Then we're basically writing a 0 back to the core, which is what our sense xy pulse function is doing. So this is reading out a single byte, 1 bit at a time, and restoring the bits back to the previous state if it needs to. And we've got some other stuff here. This is all just serial print stuff. This echoes information back to the GUI, and at the very end I'm using a token of end, which tells us that the information being sent to the GUI has completed. There's a write ability here, write command, and this is very similar to the read command, except now all we're doing is simply writing the data to the core without any regard for reading the data back. It's really very simple. Okay, again with end instructions there. Our F command is fill, which basically means we can fill it with any byte that we like. So we're actually sending a byte in the string that calls this, and it comes into, again, value of data earlier on. So all we're really doing is just like before, but this time the data is anything we like. We can fill it for the FF, we can fill it for 00, 55, or AA, which gives all of the 1-0 combinations that you could possibly want, or any other arbitrary character that you want from 0 to 255, and it basically fills the entire memory with that pattern. S command is a string, and all we're really doing yet again is taking the data, except this time it's ASCII string data. Doesn't have to be 0 to 255, and it's just characters within the ASCII character set. And this time again we're looping through and writing them straight to memory, but it's coming from a string. It's actually being read from here. You'll notice we've got input string, which is our string coming in of the address that we're selecting. We're taking the char of that, in other words 1 byte at a time. The data of that char is conveniently called data, and this is the write out to the core of that data. So that's just basically, again, filling you can think of it like a fill memory, but this time it's filling with ASCII data, if you like. So we're taking the char of that and filling it, rather than sending raw binary. And we've got a little bit of echoing back there. Yeah, that's all good. Everything else is pretty much what you've already seen. This is our serial event, data coming in from the GUI to the Arduino. We're basically reading it into a buffer that we've created. This is our probably the most important part of the whole thing. This is the piece of code, the function, which writes and reads to the core itself. What's happening here, we're setting up inputs of whether it's a read or a write bit. In other words, is the polarity going to go forward or is the polarity going to go backwards? You can kind of think of it the same thing. Is it a read or is it a write? We are taking 2 inputs as well, byte X and byte Y. Those are our addressing or select line data coming in. I've got all of the mapping to the lines from our XY data. It's been remapped to the appropriate pins on the Arduino, and I won't explain this all. It's basically just making sure that the lines go to the appropriate pins on the Arduino. It was really just so you didn't have wires crossing and that sort of thing. It all comes out the right pins. And then we've got the read-write bit here, our mode if you like, whether it's a read or a write or 1 or a 0. And again, we're setting everything up ready for the pulse, whether it's a write pulse or whether it's a read pulse. We can then switch off all of the interrupts within the Arduino, so we don't get affected by anything else that might be running along the lines of that. At this point, we are writing data to our ports for the X and for the Y decode lines. So now we're actually taking our previously calculated D and B variables, putting them straight into ports D and B accordingly. At this point, we can set on the current for either the Q1 or the Q0 lines. Now the Q1 or the Q0, if you remember, are the actual triggers which will switch on current to the drive lines to the core. So really all we're doing is putting the port B on. In other words, writing the Q state, whether it's Q1 or Q0. So at this point we've now got current flowing. We've got current on at this point through cores. If you remember, we don't want the current on too long or too short. We've got a little delay here of roughly about 500 nanoseconds. It's adjustable. You know, you can add these knobs, or you can take some away, and you can move around the exact point where we're going to sample the sense amplifier output. It takes a bit of time to get the reaction back from the ferrite core. When the ferrite core does eventually react, we are reading the sense data here, and that comes into our variable S. Variable S, standing for sense, is the logic level of whether the ferrite core flipped state or not. You'll notice I've got a couple of these little port C. This is our analog A0 line. I think it's A0, is it for A5? I forget now. Where actually it gives our output for a scope. And we've got some delay cycles. This is roughly, it's not critical, but it's roughly about 1 microsecond. This basically allows the whole thing to settle down after the sense, and allows the sense amplifier some time to recover, because it's quite a big pulse. You know, when it comes through rough, and then you've actually got to have time for the sense amp to calm down and go back to its logical state. So that's a delay for that. Now when we're done, we then have to turn both Q lines off. That's Q0 and Q1. If you remember, those are our trigger lines to put current on. We are now turning current off. And at the very end, I've just got a bit of a fail-safe delay. Just put another sort of 1 microsecond in here, roughly. And all this really does is allow more time for the sense amplifier to recover. Because when we call this the next time, there is no delay at the beginning of the code, you'll notice, except, you know, we're putting the address on straight away. There's no delay coming into here, so we'll put the delay at the end, and every time we run through here we're guaranteed a bit of a delay before this is executed. Alright, and that is really the code. At the very end we turn the interrupts back on again, and that resumes all of the interrupt services within the Arduino to do anything else that it needs to do. So the next thing we're going to look at is the other end of the USB cable, and that's going to be the GUI for our graphical display. So let's take a look at that now. Right, so continuing on the theme of the software, I've put together a GUI, graphical user interface, which means we can put it on our PC desktop and interact with the Arduino over the USB cable. What I'll do is I'll show you the main form. I'm not going to go through all of this code. It's just standard C++ stuff for handling serial port, and also displaying, you know, interpreting bytes, and you know, separating them down to bit level. You really don't need to go through all of this unless you absolutely want me to. But it's all a bit not necessary to cover for the purposes of this project. It's basically just a front end, and you know, we're reading in serial data and parsing it and extracting bits and that sort of thing and putting it to the screen. And what we do have here is a form, and I've put this together. This is the front form for the application. You notice we've got like a grid here and some buttons, and we've got a couple of log windows and some displays down here. Now when you compile all of this, you end up with a working GUI exe file, if you like, in an application, and I'll show you that right now. So I'll just close this down, and I've already got it here. So this is actually the application once it's compiled, and here we go. So now this is a working application. Core memory front end terminal. I couldn't think of anything else to call it. So there you go, and it works through a COM port at a baud rate of 19,200 baud in this particular case, and we're offline. Now what I will do shortly is connect this all up and we'll see it all operating, but just for now I'll just tell you basically what's going on. This grid here, which you may have probably realized, is 16 by 18, and each one of these squares, these cells, are representing individual cores or bits within the core memory device. So these are actually going to be displaying our bit information from the core. We can read out all of the data from the core. If I click that, it probably says I need to connect. Yeah, I'm not connected. So if you can read out all of the data, that does an entire core dump and graphically displays ones and zeros on this grid. And we've got a log window here which will show us some logging information. If you remember, there's some serial data sending, like logging human readable sort of sentences coming from the Arduino. That all shows up here. And if we write a string down here, and I'll just type in some complete gibberish here, we type in a string here. When you write a string here, that is sent to the Arduino, which then sends it to the core. And when you read out the core, the data will appear here on the ASCII string logging window. It's kind of extracted from the command data that's sent to us, and we end up with just basic or very simple ASCII strings that we can actually read. So this is our front end, just to familiarize it with it. And I've got a few things here. You can write patterns of 010101, or you can write patterns of 1010, so you can flip every single state. Worst case scenario, you can flick them backwards and forwards as many times as you like. You can set all the bits to 0, or you can set all the bits to 1, and it's all very handy for just basically making sure the whole thing works. So those are sort of like testing buttons, if you like, and we can clear the display there, and that is our little GUI. Okay, so let's go and plug things in and let's have a play with it. Let's see if it works.
Okay, it's getting exciting. So here we are, fully populated board, and there's the core store unit, of course. There's the little preset that I've had to add for the sensitivity gain. We've changed the two limiting resistors for the current, for the half current. You probably can't see from this angle, but there's lots of resistors underneath here, underneath the core store. That's all of the other limiting resistors for the modification that we did to fix the problem. So the whole thing's ready to go. Ribbon cable connecting to the Arduino development board over there. Pretty much all straight except for the power lines, but everything else is straight through. USB connection to the PC. We are ready to switch it on and give this a try.
Okay, so the core store is connected to the Arduino, and the Arduino is connected to the PC. We've got our regulated 5V supply driving the core board. We are ready to go. Let's give this a try. So let's open up our GUI front end, and the first thing we need to do is to connect to the Arduino. So let's hit the connect button here, and we're on COM5 in this case, so we'll just connect. Now we are connected. Right. We need to give this a try. So first of all, let's just press clear there. I'm going to try writing all zeros. Okay, memory filled. We've just, well, hopefully, let's give this a try, and let's read out the core. Alright, look at that. So far so good. All zeros. These are all the bits within the core, as we talked about earlier, 16 by 18 matrix. And I can look at the actual responded hex data here, and it is all zeros. Well, that's good. Let's try writing all ones. All ones. Let's read out the core. Yes, perfect. So I've got to scroll down a bit here. There you go. FFs. See all these FFs here? That's absolutely great. So now we've got control over the core. Let's try a 0-1 pattern. That's filled it with 0101 all the way through, and read that. There it is. Zeros, ones, zeros, ones, all the way through. And we can look at the hex data down here. It's all 55. That's correct. That's 0 ones in ASCII, in hexadecimal. I beg your pardon. Okay, let's try the other state. 1 0. That's an inversion of what we just had. And again, it's ones, zeros, ones. It's working. That's fantastic. So now we've got AA as hex for the result. That's correct. Wow. So we are now writing to the entire core store, and it appears, I'll try zeros again. There you go. That's all zeros. Everything looks good. And then we'll flip it all to ones. Let's just play with this now. Fun time. That's all ones. That's perfect. Okay, so it's actually working. So what we need to do now is we can play a little bit further. Let's try sending a string to the let's try sending a string to the core device. So let's say something like, no, don't forget, I've only got 36 characters. Can't just the memory will only handle so many characters, and I think we're limited to 36 because it's 288 bits divided by 8. So let's have a go. Let's say hello. Whoopsie daisy, hang on. Hello YouTube. Is this working? Right. Hello YouTube, is this working? Now what should happen is, I hope that's not 35. Let's write a string. It says string is written. Let's read out the core. And there it is, ladies and gentlemen. My screen definition is brilliant, but hopefully you can see that. This is the output log window, and there it is. Hello YouTube, is this working? Fantastic. So we actually sent the data in here, and it came out here. This is the read command coming back from the core. Cool. And this is the binary representation of all of the cells that were filled, all the cores that we've flipped. For instance, if you look at X0, Y0, which is this one here, you'll see it's a 0, and so on. Now, the way this is mapped out is these first 8 bits here, this first byte, that's the first byte of the string, and then the second byte of the string is actually these 8 bits here. So we've got, if you like, byte 0, byte 1, byte 2 is here, yeah, byte 3 is there, and so on all the way through to byte 35. I think I've got that right. So yeah, and that's how the characters are actually represented within the core. You could have done this another way. You could have decided, well, I'm going to do 8 bytes this way, and you know, and maybe do another 8 bytes this way. But then you've got like this extra 2. You'd have 16 bits plus 2, and you wouldn't know what to do with those. Maybe use them for some other purpose. But yeah, actually, the whole thing's actually working. So let's try something different. Let's just I don't know, the quick brown fox jumps over the lazy dog. Oh, I've missed a character out. Wait a second. Quick brown fox jumps over the... And those of you who go back to days of teletype machines and what have you, will realise that that's all the letters of the alphabet in one sentence. So let's send that. I'm going to clear it by writing zeros first. Okay, right, now we're all clear. Everything's 0. Now let's write the string and read it back. And there it is. Perfect. Quick brown fox jumps over the lazy dog. And that little character on the end is because... Why would that be because? I think it's probably because of the... there'll be a carriage return at the end of this, or actually it'll be a string null, which is 0. It's probably just a 0 at the end. Is that right? Let's have a look. It would be that character there. So oh, we could look at the hex, couldn't we? OA. You see that last character there? OA. That is I think it's a new line character, either carriage return or new line. And so that's actually what that is. When we're sending it, we're actually sending it with a carriage return or a new line character at the very end. You just don't see it, but that's what that little character is right at the very end. It's a hex 0A, and that's our last character. You can see it's 0A if you look at the actual binary. Yeah, so it's 0A 1010. If you like 10 in decimal, that's 8 in hex, which is our new line character at the end, and that's what that little character is at the very end. So yeah, perfect. And every time we click read, we should get continuous output here. It's just all exactly the same. So that's fantastic. So this has been a journey. We've gone all the way through from designing from a single bit in the previous video to this, which is now writing to the entire core, and we can pretty much manipulate it any which way we want over USB. And I'm just reading it back there. We can write it with all ones. There you go, it's all good. I'll just get rid of that blue square and clear it up. You know, we can write 1-0 patterns. Clear that up. Yeah, or we can write 0-1s. So I can flip them between 1-0 and 0-1 and 1-0 and 0-1, and it's perfect. So yes, absolutely fine. And there's only one thing I can say to you now, which is goodbye and see you next time. Let's put that in the core store after we've done a clear, and write the string and read it out. There it is. Okay, thanks very much for watching, and it's been again, it's been quite a journey, and I hope you stuck it all the way through to the end. We've covered a lot of stuff, and we're going to leave it right there. So we'll see you all next time. Goodbye.